All right, let's get into it. Today, we're going to peel back the digital layer on the maps that you use every single day on your phone. We're going to see the absolutely ingenious systems that make them tick. It's a journey from really simple grids to some pretty complex shapes, all in this quest to perfectly digitize our planet.
I mean, think about it for a second. You open an app, you tap the nearby button, and boom, instantly it shows you cafes, parks, whatever you're looking for. How on earth does it search through billions of possible locations across the entire globe in just a fraction of a second? Well, the answer is a very clever trick for giving every single spot on Earth its own little digital address. And that trick, that whole field, is called geospatial indexing. At its heart, it's all about translation. You take a two-dimensional location, your classic latitude and longitude, and you figure out how to squash it down into a simple, one-dimensional string of letters and numbers. And why do you do that? Because databases are absolute wizards at searching through a simple list, but they are just terrible at trying to understand a 2D map.
So the mission was clear, at least for the developers. They had to create a digital address system for the entire globe, one that a computer could read as easily as you or I would read a shopping list.
And this really lays out the core challenge, the fundamental puzzle. We live in this beautiful, spherical, two-dimensional world, but our databases, they work best with flat, one-dimensional data. So how in the world do you bridge that gap without losing the most critical piece of information? What's actually next to what?
So the first really popular solution to this problem showed up back in 2008. It was this elegantly simple system called Geohash, and it really laid the foundation for everything that would come after.
Okay, so the way it works is actually wonderfully straightforward. Imagine you've got a map of the whole world in front of you. First, you just cut it in half vertically, right along the prime meridian. Is your location on the left? Okay, that's a 0. Is it on the right? That's a 1. Now take that half you're in and cut it horizontally, along the equator. Are you in the bottom half? That's another 0. Top half? That's a 1. And you just keep doing this over and over. Cut, check, building this long string of 1s and 0s. Then, that binary string gets converted into a much shorter, easier to handle code.
So, a very specific point, let's say somewhere near the tip of Denmark, goes from being two long, very precise numbers into this single compact string, U4PRUYDQQVJ. That's it. That's the location's digital address.
Now here's the real secret sauce, the genius of the whole system. If two different locations have geohash codes that start with the same letters, like they both start with U4PR, you know for a fact that they're in the same general neighborhood. And the longer that shared piece at the beginning is, the closer they are. This is amazing. It turns a really complex 2D distance problem into a simple text search, which for a computer is lightning fast.
But, as elegant as Geohash was, it wasn't perfect, not by a long shot. This simple grid system had some pretty fundamental flaws that, in some cases, could cause really big problems.
Okay, here's the biggest issue, what's known as the edge case problem. Imagine two houses right across the street from each other. But that street just happens to be one of those big dividing lines, like the equator or the prime meridian. In the weird world of Geohash, one house might have a code that starts with U, and the one right next to it could start with G. To the database, these 2 points look like they are on opposite sides of the planet, even though you could literally throw a rock from one to the other. And that makes finding what's nearby really tricky at these boundaries.
And the second big problem is distortion. Geohash basically treats the world like it's a flat, rectangular piece of paper, but the Earth isn't flat. A degree of longitude at the equator is huge. It covers about 111 kilometers. But way up near the poles, that same degree of longitude might only cover a few meters. This means the Geohash grid cells get all stretched out and weird-looking. They're not nice uniform squares, which makes calculating distances really inconsistent.
So look, Geohash was a fantastic first step. It solved a massive problem with a really simple, clever idea. But its flaws were pretty obvious, and it left engineers everywhere asking, surely we can do better, right? Could we build something smarter?
And the answer, of course, was a resounding yes. This kicked off the development of much smarter grids, with two major new systems coming from Google and Uber, designed specifically to fix the problems that Geohash had. First up to the plate is Google's S2 system. It was released in 2017, and it basically looked at Geohash's two main weaknesses and tackled them head-on with a couple of really clever innovations.
The first big change is the path the index follows. Geohash fills space with this kind of jagged, zigzagging Z-shape, and that's what creates those really harsh edge cases we talked about. S2 throws that out and replaces it with something called a Hilbert curve, which is a much smoother, continuously flowing U-shaped path. This gentler curve does a way better job of keeping points that are close in the real world, close together in the index, which dramatically reduces those sudden, crazy jumps across the map.
Second, to fix that distortion problem, S2 stops pretending the Earth is a flat rectangle. Instead, it projects the entire globe onto the 6 faces of a cube, and then it unfolds it. Now, since a cube is much, much closer to being a sphere than a flat sheet of paper is, this move drastically reduces how much the grid cells vary in size, especially up near the poles.
Then, just a year later, Uber comes along and releases H3. And they took an even more radical step. They decided the problem wasn't just the path or the projection, it was the fundamental shape of the grid cells themselves. So they just threw out the squares.
And they replaced them with hexagons. So why hexagons? Well, it turns out hexagons have this unique, almost magical property. Every single one of a hexagon's neighbors is the exact same distance away from its center. Think about a square. It has neighbors on its edges, and then it has neighbors on its corners. That's 2 different distances. For a company like Uber, which is constantly trying to calculate things like the nearest driver or where to apply search pricing, the uniform distance of hexagons makes all that math dramatically simpler and faster.
H3 also ups the game on the projection. Instead of a 6-sided cube, it uses a 20-sided icosahedron. And the logic here is pretty simple. The more faces a 3D shape has, the closer it is to being a perfect sphere. And this means H3's hexagonal cells have even less size distortion across the globe than S2's squares do.
Okay, so with all these incredible innovations, which system is actually the best? Well, like with most things in engineering, it's not really about being the best. It's about making the smartest trade-offs for what you need to do.
So let's look at the final scorecard here. Geohash is super simple, but suffers from that large distortion. S2 comes in and improves on this big time with its cube projection and much better pathing. And then H3 has the most uniform cells and that incredible benefit of equidistant neighbors. But notice the trade-offs. To get those perfect hexagons, H3 has to sacrifice the strict parent-child hierarchy that Geohash and S2 have. In H3, a point inside a tiny hexagon isn't guaranteed to also be inside that hexagon's larger parent cell. And for some applications, that can be a problem.
So the real takeaway here is this. There is no single best system. The choice you make depends entirely on the specific problem you're trying to solve. If you absolutely need a strict hierarchy where cells nest perfectly inside each other, Geohash or S2 is probably your tool. But if you're doing complex analysis that needs uniform areas and really simple neighbor finding, like Uber was, then H3 is the clear winner.
It's pretty amazing when you think about it. This whole evolution, from a really simple grid to covering the entire globe in hexagons, it all happened in the span of about a decade. It just shows this relentless drive to model our physical world more and more perfectly in the digital realm. And it leaves us with a really fascinating question to think about. What shape comes next?